So, the next topic we will get into discussing is something called as a PN junction, and it is also a junction that we sort of looked at earlier on when we just when we discussed the concepts behind how to create band diagrams, etc. As I mentioned, the PN junction is actually a junction created between a P type semiconductor and an N type semiconductor. Now, if the semiconductor is the same, you will end up with these two materials having band diagrams of this kind. So, you have your conduction band edge, you have your valence band edge, and since it is a P type material, you have a Fermi level that is located slightly below the intrinsic Fermi level, and this depends upon the doping density. And in the case of an N type semiconductor, you have your valence band, your conduction band, and you have a Fermi level that is above the intrinsic Fermi level position. Now, since the semiconductor is the same, your electron affinity is also the same. So, if you were to create a junction between these two semiconductors, if you recollect the idea behind drawing band bending diagrams, we need to understand how the electrons would flow. So, in this case, the Fermi level here for the N type semiconductor is higher than the Fermi level position for a P type semiconductor, and therefore which basically implies that the work function of the N type semiconductor is smaller than the work function of a P type semiconductor, and therefore the electrons will flow from the N side to the P side. And therefore, if you have to construct this junction, what we will see is that in the N type material near the junction is lost electrons, and therefore the conduction band edge moves away from the Fermi level, whereas the valence band edge moves towards the Fermi level, whereas on the P side the interface has gained electrons. So, you have added electrons to the P side, and therefore the conduction band edge moves towards the Fermi level while the valence band edge moves away from the Fermi level. Now, throughout this band bending diagram, your energy gap is more or less constant, your electron affinity is constant, and far away from the interface, that is very far from the junction, the semiconductor really does not notice any effect of the other type of semiconductor or the effect of the junction, and therefore you have your typical N type bulk material and your P type bulk material. So, this is the PN junction diagram, okay, the PN junction band bending diagram. So, the Fermi level is aligned as is required for at thermal equilibrium. So, this is true only at thermal equilibrium, and you have this kind of a band bending diagram, and just as in the case of metal semiconductor junctions, we can define the electric field in this region. We can define something called as a built-in potential, that is effectively the potential difference between due to this band bending, okay. So, that is the built-in potential, and now we will try to use Poisson's equation to try and understand what the electric field is and what the built-in potential is, okay. And that will be the first exercise we will go through, and we will also define some coordinates, because these regions near the interface, okay, if you look at this, okay, let me just draw a dotted line here and a dotted line here. Now, if you think about this region, on the N side it has lost electrons, and it did not have many holes to begin with. So, in some sense this region is depleted of free carriers, and on the P side it has gained electrons which would have recombined with all the holes, because it had a lot of holes, but since these electrons have come in, the holes and the whole population is also scanty now, okay. And if you want, you could think of it as the holes having diffused to the N side, okay. And the electron population was not very large to begin with, because here the whole population was approximately Ni square by Nd, and there the electron population was Ni square by Na, and therefore those numbers are not very large to begin with, and therefore this region is also depleted. So everywhere you see a band bending, you could say that the region is devoid of free carriers. Now in reality it's not completely depleted, you do have free carrier concentration, and the electron and hole concentration can be identified by looking at the difference between the Fermi level and the conduction band edge, or the Fermi level and the valence band edge respectively. But if you assume it's depleted, it makes your your solution for the electrostatics a lot simpler, and we will start with that assumption. Okay, but in the metal semiconductor junction, when we already looked at a very general Poisson equation wherein we considered the electrons, we considered the whole population, we considered the dopant ions, and we did solve Poisson's equation. So you are already familiar with what to do if you have to consider everything. But for the case of for this analysis, we will just assume it's a depleted region. So if it's depleted, what is the charge concentration? On the n side, you have all the positively charged fixed donor ions. Okay, so these had donated electrons to the n type material, and those electrons have all diffused onto the p side, and therefore these are fixed donor ions. And on the p side, you have the negatively charged fixed acceptor ions. So these are the acceptor dopants that gave up that took in an electron and essentially gave up a hole, and those holes have now diffused to the n side, and therefore you have exposed acceptor ions. So this is the situation. You have a depleted region where you have a charge concentration here which is basically plus q Nd, where Nd is the number of dopants per unit volume, and the charge concentration in the p region is minus q Na, where Na is the number of acceptor ions per unit volume. So if we have to write Poisson's equation for the n and p side, what would it be? Poisson's equation tells you that dE by, so we are looking at only one dimensional cases here. So dE by dx, where this is the electric field, is equal to your charge concentration by epsilon s, where this is the permittivity of the semiconductor. So the charge for the n side, your Poisson's equation is going to be dEn by dx, the subscript n is to denote the n side, is equal to your charge concentration on the n side, which is q Nd by epsilon s. And for the p side, you have a Poisson equation which is dP by dx is equal to minus q Na by epsilon s. So this is these are the equations that we need to solve to understand the electrostatics. And what we will do is we will solve for the n and p side separately. Okay. So on the n side, you have your Poisson equation as this, which is quite straightforward because this is a constant. Okay, and it's a constant because we have not considered the n and p, the free carriers, and therefore the electric field is simply given by this term here. And you will already recognize that a boundary condition has been applied. Okay, and what was the boundary condition? Since on the n side, if you only look at the n side, we can draw the band bending diagram as this. Okay, so that's only the n side of it, and that's your Fermi level. And we say that at x equal to xdn, all the band bending has stopped and the bands have now become flat, and therefore at this edge the electric field is 0. Okay, and it's only within this region from say x equal to 0, which is being defined at the junction, to x equal to xdn, that you have any electric field. And if you say electric field is 0 at x equal to xdn, then you apply this boundary condition to this to the solution, and you end up with the electric field being this particular term here. And the potential, if you look at the potential, since the electric field is nothing but the derivative of the potential, is the negative of the derivative of the potential, you can now find the potential function as well, which is going to give you a quadratic relation of this kind. Then on the p side, you have your Poisson equation to be defined by this expression, where this is the charge concentration. Na is all negatively charged ions, and therefore you have a negative sign, and you apply the boundary condition. If you look at the p side, you have a band bending that looks like this. Okay, let me just be a bit more accurate. That looks like that. And on the p side, since this is my x equal to 0, we have band bending till a point of x is equal to minus x dp. Okay. So, this side of the axis is all negative values of x, and that is all positive values of x, and you apply that boundary condition and you will end up with this solution to your electric field. And now you can go ahead and calculate the potential. So, the expression for the potential would be another quadratic which is telling you what is the potential on the p side. So, since there has to be a continuity in the electric field, now we have solved for the electric field on the n side and the p side separately, right. On the n side, we got an expression which was qnd by epsilon s into x minus xdn, which means at x equal to 0 my electric field is negative. So, En is negative, and it says it is minus qnd xdn by epsilon s. So, that is my electric field on the n side at x equal to 0. And if you use the expression for the electric field on the p side, if you substitute x equal to 0, you end up with an expression of Ep at x equal to 0 is minus q n a x dp by epsilon s. Now, that we are talking about the same field, okay, for the field has to be continuous. So, you have an electric field that varies like this and varies in this manner, with that being your xdn and that being your minus xdp. So, since at x equal to 0 En has to be continuous, you have En at x equal to 0 being your Ep at x equal to 0, which gives us a very important relation that your Nd into xdn must be equal to Na into xdp. So, what does this relation mean intuitively? It means that if my dopant concentration is large, okay, let us say Na is much larger than Nd, it says that xdp is going to be much smaller than xdn, which means it takes a lot less distance for me to shield all the field, okay, because my charge concentration is very large. I just need a smaller amount of charge exposed before all the electric field is nullified. Okay. On the other hand, if my charge concentration is very low, I need to expose a lot more charge before the electric field is nullified. So, that is essentially what this expression intuitively implies. And now, we also know the potential, okay, in the n side and on the p side from our Poisson's equation. So, if we set a reference potential, so let us say we set a reference potential at x equal to minus x dp. You could set a reference potential anywhere, but we say that this point has got a potential of 0, and therefore, this entire potential difference between here and x equal to xdn is my built in potential. So, that potential is my phi n at xdn minus phi p at minus xdp, which is my reference. So, that is my reference potential. And you substitute for these two values of x, you say x equal to xdn there, and you say x equal to minus xdp here, and you solve for the potential and you calculate this difference, and you will end up with this expression for the built in potential. So, it depends on the square of xdn and xdp. Okay. So, this is a bit about the electrostatics of your p-n junction, which is obtained from your Poisson's equation. Now, taking this one step further, so that is my potential term, right, but we already know. So, let us make use of point number 1 in this expression. that is ND into XDN is equal to NA into XDP. So let us make use of that. Since we already know that, we can write your XDN in terms of XDP alone or vice versa, and using that in your potential expression, using that in your expression for phi bi, we can estimate what XDN and XDP are in terms of phi bi. Okay, you will find that your XDN has got this dependence on the built-in potential and your XDP has got this dependence on the built-in potential, and therefore the total depletion width, that is taking into account the P and N side, okay, the total depletion width that we call as XD is equal to XDN plus XDP. So that is your XDN, that is XDP, and this sum is simply the sum of these two terms, and you end up with this expression. So these are all very useful expressions for you to perform quick calculations. Okay. So even though we have not made, we have assumed that these regions are devoid of free carriers, we did not take into account N and P, because if we do take this into account, these will all be functions of the potential, and therefore your Poisson's equation will have a nature of this kind. It will be some function of the potential. So just to summarize what we looked at in the electrostatics, do forgive me if this writing is too small. We saw that this is the N side and that was your P side, and once the junction is created, you have a band bending diagram that looks like this. And if you look at the charge profile versus distance, you have all the exposed donor ions exposed there, and you have all the acceptor ions exposed here. And since our donor dopant concentration was constant, right, it was not varying with space, this is constant with space and that is constant with space. And the electric field profile looked like this. Okay, we saw that it had a relation of X minus XDN on the N side, and is proportional to X plus XDP on the P side, with X being a negative term. And if you looked at the built-in potential, we had set this as a reference of 0, and the built-in potential slowly increased as you went from the P to the N side. So this is a summary of the electrostatics of a PN junction. So now let us look at the current voltage characteristics, and before we do that, we need to see what happens when we take the system out of equilibrium. So this is all at equilibrium. Okay, it is only at equilibrium the Fermi level aligns when you create a junction. So when we take it out of equilibrium, let us do so by applying a voltage. Okay, so we are going to now apply a voltage across the PN junction, and the voltage is being applied in a manner where the plus is toward the P side is at a higher potential as compared to the N side. If the voltage on the P side, or as we have drawn this picture, if my VA is greater than 0, that is the voltage on the P side is greater than that on the N side, then the device is supposed to be in forward bias. And if the voltage is less than 0, then the device is said to be in reverse bias. And if the voltage is equal to 0, then you are at equilibrium. So everything we have discussed so far is all at equilibrium. There was no voltage applied, or in other words, VA was equal to 0. But now when you start applying a forward bias or a reverse bias, that you start taking VA to be non-zero, then your built-in potential changes a little. Okay, and we have already looked at it in the metal semiconductor junction. You see, these relations are quite familiar, are quite similar to your metal semiconductor junction relations, except for the fact that you have both an Na and Nd doping, etc. But you will see that all the other terms are quite familiar. Okay. So just like in that case, you can take an intuitive leap by noting that your built-in potential term will now at equilibrium, instead of using the equilibrium value, we replace that with phi bi minus Va in order to calculate your new xdn and your new xdp and your new xd. So, instead of just using phi bi, we replace that with phi bi minus Va, where Va is the applied voltage in order to get your out of equilibrium values. So, which means what? Which means that when my Va is positive, my xd decreases, both my depletion widths, the xdn and xdp decrease and my total xd decreases. And in reverse bias, when my Va is negative, if Va is less than 0, then phi bi minus Va is going to be a larger number and my depletion widths would increase. Okay. So, to give you an intuitive feel again, just to summarize what non-equilibrium does. So, let us say, let me sort of draw this much more clearly. So, let us say that was my equilibrium case, okay, that is the band bending in equilibrium. So, that was the value of xdn. So, let us say my x equal to 0 is somewhere here, and that is my x equal to minus xdp, and that was the built in potential right there. So, this is all at equilibrium. Now, when we shift it out of equilibrium, the band bending changes a little. So, you firstly make the bands a little bit more shallow, okay, because the built in potential will now become phi bi minus Va. So, in forward bias the band bending will be a little shallower and the depletion region is only going to be extending from here to here. It is not going to be as large as before, it is going to be much smaller. On the other hand, if it is reverse bias, the band bending will be a little bit more steeper because my phi bi is increased and it will also extend to a larger distance. Okay, so, that is going to be the reverse bias case. That is going to be the equilibrium, that is going to be the forward bias case, and that is going to be the equilibrium case. So, that is sort of intuitively summarized, and if you look at the electric field profile in forward bias, it is going to be something like this because the depletion widths have now reduced and the built in potential in forward bias is of course going to be less, it is going to be phi bi minus Va, and in reverse bias it is going to be larger because your Va is negative. So, now let us start heading towards understanding the current voltage characteristics. So, what defines the current voltage characteristics in a PN junction? So, at equilibrium, so let me just draw the equilibrium band bending diagram. So, if you think about the N side, it has a lot of electrons, okay, so that is my built in potential there. It has a lot of electrons and I'll just in a very poetic manner, let me just show you all these electrons as a big heap of electrons there, and it has got very few holes, okay. So, these are all just holes, but a lot more electrons and these are all sitting there. On the other hand, the P side has got a lot of holes, okay. We need to mark these differently. So, the electrons are all marked as solid objects and the holes are all these hollow circles. It has got a lot of holes, on the P side has got a lot of holes and very few electrons. Now, if you look at the electrons on the N side, they are trying to climb up the hill, okay. If you look at this, if you look at the band bending, if you recollect, the band bending diagram is all drawn in a manner where you know it's easy to understand the motion of the electron and hole. The electrons like to run downhill, the holes like to run up the hills, and you know, if you increase the potential the energy levels go down, and if you decrease the potential the energy level goes up, okay. So, that is the way you imagine the band diagram. So, these electrons on the n side have to overcome this barrier. Okay, they have to overcome this barrier in order to get to the p side. On the other hand, the electrons on the p side will just try to run down the hill towards the n side. So the electrons on the p side will try to drift down, whereas the electrons on the n side have to diffuse across, and they can do so only if there are a larger number of electrons sitting above this barrier, okay, very intuitively. And it is a similar idea on the p side, or if you look at the picture of the holes. So essentially at equilibrium there is no current, okay. The electron current is 0, the hole current is 0, and the total current is 0. That is because the electrons that are drifting towards from the p to the n and the holes that are drifting from the n to the p are balanced by any diffusion of electrons from the n to the p and any diffusion of holes from the p to the n. So all these currents are essentially 0. But the moment I reduce the barrier height, so let us say we apply a forward bias and we reduce the barrier height. So let us sort of redraw this picture. The moment the band bending shifts to a shallower built in potential, so by applying forward bias, this heap of electrons now protrudes significantly above this much lower barrier height, okay, and a lot of electrons start diffusing from the n to the p side. On the other hand, the drift of electrons from the p to the n side does change, but the change is not that significant, okay, and therefore the current is heavily dominated by the diffusion of electrons from the n to the p side and the diffusion of holes from the p to the n side. So just like the barrier height was lowered in the conduction band, the barrier height is also lowered on the valence band, and you have a new picture of this kind. So you have a lot, these holes now have to diffuse across this much lower barrier, and therefore the diffusion of the holes increases. Okay, so you will find that in forward bias the electron current goes to greater than 0, and this electron current is composed of diffusion and drift, and it is the diffusion component that dominates. Similarly, the hole current goes to be greater than 0, and it is the diffusion of holes that dominates. Okay, the drift has not changed too much, and therefore in effect what this implies is there is a huge amount of transfer of electrons from the n to the p side and holes from the p to the n side. And since we had biased our p-n junction in this manner, wherein the voltage is positive here and it's negative in the n side, which means it is forward biased, you have a lot of electrons moving here, you have a lot of holes moving this side, which means you have an large effective current going from the positive terminal of the battery through the p-n junction to the negative terminal of the battery. So it is a very large current that goes through, and a small increase in VA reduces the barrier height a little, but since the diffusion component or the the electron population is exponentially dependent on the voltage, you find that the electron population scales up much large, it scales up very rapidly as you change the value of VA. Therefore, the diffusion is quite a powerful component in the current. Now on the other hand, okay, if you say let us not apply forward bias, let us apply reverse bias, which means that my VA is negative and the N side has got a larger potential as compared to the P side. Then in that case the band bending will become much more steeper, okay, and there will be only few electrons peeping up, only few electrons diffusing from the N to the P side and very few holes diffusing from the P to the N side, whereas the drift once again has not changed too much, but it has definitely been impacted, and you will find that the drift current dominates. The magnitude of Jn is still greater than 0, but it is the drift component that is important now. The diffusion component is not so important. And similarly for the P side, the drift component is important, but the diffusion component is not important, because you have now increased the barrier height by applying a reverse bias. So what does electron drift do? Since the electric field has now become larger, okay, because of the reverse bias, you will find that the electrons drift from the p to the n side and the holes drift from the n to the p side, and that is the current that is important. So this is the scenario. You have your p-n junction, you have a voltage source that is now negative. So let me put a negative sign then positive, or maybe I should just retain the old convention and just say VA is less than 0, okay, which effectively implies that that side is a negative and this side is a positive, okay. Or once again, let me just make it, just to make things very clear, let me apply a battery like that, okay. So that solves everything, and you find that the electrons drift from the p to the n side. So that is my current, and I have holes drifting from n to the p side, which means that you have a current flowing this way from the n to the p, okay, and that is my effective current in the p-n junction, and this current is not very large, it is not as prominent. So if I were to apply the same amount of forward and reverse bias, if I say that the magnitude of VA is same, and in one case I apply, let us say, just for the sake of example, let us say I apply plus 1 volt, and in the other case I apply minus 1 volt. Yes, I will have currents in the forward and reverse direction, but the forward direction current will be much larger, because the electron population scales exponentially, whereas here it is only the field that is determining the current, it is a drift current, and therefore the forward bias current at 1 volt will be much larger than the reverse bias current at minus 1 volt, okay. And we will sort of mathematically now sort of bring in all these arguments, all these qualitative arguments in a more mathematical description, in a manner which is quite similar to what we did for metal semiconductor junctions, but we will just look at some of the important differences between the metal semiconductor Schottky junction and the p-n junction diode. Okay, so one point which is obvious from what I told you, but needs to be mentioned, is since the current in forward bias is going to be much larger than the current in reverse bias, you do have a rectifying nature for the p-n junction. So you will find that the current voltage characteristics for a p-n junction looks like this, wherein when my bias goes to be greater than 0, the current scales quite rapidly, it is an exponential dependence on the voltage, and when it is less than 0, it is still an exponential dependence on the voltage, but it is exponential of a negative term, okay. So it is going to be dependent on this term there and dependent on this term here, and we will see this come out in the mathematics of it, okay. So therefore the diode rectifies, it has got a rectifying property, it allows current in one direction but does not encourage current in the other direction, while although it does allow that current.